30% of users timed out reading a popular playlist. The root cause? A hot partition in Cassandra that exceeded the 100 MB limit, triggering compaction storms. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Design Spotify. Designing Spotify means building a distributed system that scales. It involves microservices, specialized databases, a content delivery network for audio, and event-driven pipelines for personalization. Spotify started as a monolith but split into microservices. Each service owns a domain: playlist, search, social, audio delivery. They communicate via gRPC for low latency and Kafka for async events. When a user adds a track, the playlist service writes to Cassandra and publishes a Kafka event. Search and recommendation services consume that event to update their indexes. This text diagram shows the flow. The playlist service writes to Cassandra and publishes to Kafka. Downstream services consume the event asynchronously. Playlists are write-heavy. Cassandra handles this well with a wide column model. The table uses playlisted as partition key and position as clustering column for ordered retrieval. This schema stores tracks in a playlist with a position for ordering. The application manages position. For playlist metadata, a separate table with the same partition key. Audio streaming uses a content delivery network to cache files close to users. The delivery service generates a signed URL with a short expiry. The client fetches directly from the content delivery network. The client requests a stream, gets a signed URL, and fetches from the content delivery network. The content delivery network caches the file or retrieves it from origin storage. Recommendations are generated by a batch pipeline that processes user history and track features. Results are stored in Cassandra and served to clients. This pseudocode outlines the recommendation pipeline. It reads history, computes vectors, finds similar users, and writes recommendations. Search uses Elasticsearch with a custom scoring function. Indexes are updated near real-time from Kafka events. This mapping defines the track index. The search query uses multi-match with boosted fields and sorts by popularity. Social features use Neo4j for the graph. Writes go to Neo4j and publish events to Kafka, which updates Cassandra for read-heavy workloads. This cipher query finds friends who listen to a track. Neo4j traverses relationships efficiently. Kafka is the backbone for async communication. Every significant action publishes an event. Multiple consumers process them independently. This shows the Avro schema for a track play event and how to produce and consume it. Redis caches hot data like popular playlists. Use a write-through cache, invalidate on write, repopulate on next read. This pseudocode shows caching logic. On read, check Redis. On miss, fetch from Cassandra and cache. On write, invalidate the cache. With hundreds of services, centralized monitoring is critical. Use Prometheus for metrics, Jaeger for tracing, and Elk for logs. Sample traces to keep costs down. This Go code shows how to instrument a request with OpenTelemetry. The span captures timing and errors. This is the same issue we highlighted at the start. Here's exactly why that happened. The playlist partition key was userid playlisted. For the artist's official playlist, millions of users added it, creating a hot partition. Cassandra's partition size limit was exceeded, causing compaction storms and read timeouts. The fix was to redesign the partition key with bucketing. Use a composite key like playlisted, bucketed to distribute load. Also separate metadata and tracks tables. Set GC grace seconds to 0 for faster repairs. A hot partition occurs when a single partition receives too many reads-writes. Symptoms include high latency and compaction storms. Mitigate by using a composite partition key with bucketing. This is the incident we saw earlier. The original partition key caused a hot partition. The fix uses a composite key with bucketing to distribute load. When a track is updated, you need to invalidate the content delivery network cache. Use versioned URLs to avoid cache invalidation storms. If you don't set gRPC deadlines, a slow downstream service can exhaust your connection pool. Always set a deadline and implement circuit breakers. Popular tracks get recommended to everyone, creating a feedback loop. Mitigate by downweighting popular tracks or using a popularity penalty. Always use index aliases for zero downtime reindexing. If you need to change mappings, create a new index, reindex, then swap alias. Isolate the graph database behind a microservice to prevent schema changes from affecting other services. Also cache frequently accessed queries in Redis. Always set default values for new fields in Avro schemas. Use the schema registry to enforce compatibility checks. When a popular cache expires, multiple requests may hit Cassandra simultaneously. Mitigate with a mutex lock or stale while revalidate pattern. The article mentions setting gRPC deadlines, but does not show how to propagate them across service boundaries. In production, always propagate the deadline from the incoming request to downstream gRPC calls to avoid cascading timeouts. Use context with deadline in Go or equivalent in other languages. The article discusses hot partitions, but does not provide a concrete bucketing strategy. Here is a schema that uses a composite partition key with a bucket number to distribute load for a popular playlist. The article mentions using versioned URLs for audio files, but does not explain the implementation. A common pattern is to include a content hash or version number in the URL path, e.g., /audio/track ID/content hash, OG. This avoids cache invalidation storms and ensures clients always fetch the latest version. To diagnose Cassandra read timeouts, check partition size with Node tool. If it exceeds 100 MB, redesign the partition key. Also consider reducing read consistency to 1 and adding more nodes. Let's run through some common interview questions. How does Spotify handle playlist consistency across devices? Eventual consistency via Cassandra, small delay acceptable. Why Cassandra over relational for playlists? Write-heavy, simple queries, linear scalability. What happens with hot partition? High latency, compaction storms, mitigate with composite key and bucketing. And a few frequently asked questions. What database does Spotify use for playlists? Cassandra, a distributed NoSQL database. Why Cassandra over relational? Optimized for write-heavy workloads and simple queries. How are recommendations generated? Batch pipeline using Apache Beam with collaborative filtering. To recap, use specialized databases, offload audio to content delivery network, use event-driven architecture, and cache hot data carefully. Ready to go deeper? Up next, design Zoom, then design Google Maps, then design Airbnb. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.